In this section, we're going to start taking a look at the idea of complex numbers. And complex numbers are built off the idea of imaginary numbers. An imaginary number is when you take the square root of -1. There is no real number that we can find that we can take the square root of -1, so we just define it by the imaginary unit I. And then what we can do is we can go ahead and be able to subsequently get powers of I. So if we were to square the square root, then I squared becomes -1. I cubed, which can really be written as I squared times I, but we just said that I is going to be -1, which will be -1 times I, which is -I. And then I to the fourth is going to become 1, and we can just break that into I squared times I squared, which is going to be 1 times 1. So let me go ahead and illustrate that once I erase all this. And so I to the fourth can be written as I squared times I squared, which is 1 times 1, which is 1. And that's where we get these definitions from. And so in this section, what we're going to be doing is just taking a look at the different operations that we can perform on these complex numbers. And then at the end of the section, what we're going to do is we're going to see why we might even need complex numbers. All right. A complex number is going to have a real part A and then an imaginary part B. All right, so A and B are just going to be real numbers, and the I is going to be the imaginary component. So an imaginary number just has I's in it. A complex number has a real part and a complex part to it as well. All right, so we're mainly focused on the operations that we can perform on complex numbers. And we're basically going to look at add, subtract, multiply, and divide. If we want to add complex numbers, basically just treat the I like an X and just use the rules for polynomial addition. So for instance, if we had 3 minus 2i plus 4 plus 5i, we would just combine 3 plus 4, which is 7, and then we would have -2i plus 5i, and that's going to turn into plus 3i. And that's all we have to do to be able to add two complex numbers. We just go right through and we just combine the like terms, right? So i's are like. So again, -2 and 5 just turns into 3. And then we have 4 plus 3, which is going to be 7. When we subtract, we really only have one additional step. We're just going to distribute the negative to both of the terms inside the parentheses, if there is one. So it's going to be 3 minus 7i minus 16 plus 13i. And then from there, we can just go ahead and combine like terms. So we have 3 minus 16, which is going to be a -13. And then we have -7 and positive 13 i's, which is going to be a plus 6i. Right? So that's really easy, right? All we have to do is just go back to our algebra 1 and combine like terms. If we want to multiply complex numbers, we're just going to use polynomial multiplication. And remember that at the very beginning, we said that I squared was equal to -1. So this might come into play as we go through and start multiplying i's by i's as we're going through. So let's take a look at 3 examples of this. So we first have 2i times the quantity of 5 plus 2i. And what we're going to do is we're just going to distribute. And so this is going to become 10i. So we just multiply 2 times 5, and then the I comes over. And then 2 times 2 is 4. I times I is I squared. And remember that I squared is equal to -1. And so we can write this as 10i plus 4 times -1, or another way to write this is 10i minus 4. We could also go ahead and not just distribute, but we could extend that distribution to FOIL. So we have 7 minus 3i times 2 plus 4i. We take the 7, so we have our first, and we have our outer. So that's going to be 14 plus 28i. And then we take our inner and our last for our FOIL. So that's going to be minus 6i, and then minus 12i squared for the other terms. We're going to do the exact same thing as we did before, is we're going to turn the I squared into -1, but we're also going to combine the inner terms. So this is going to become 14 plus 22i, all right? So we just add 28 and 6 to get our 22. And then we have -12 times -1, okay? Or 14 plus 22i plus 12. And then notice that we have real numbers there, or just we go through and add the constants together. So our final answer to this is going to be 26 plus 22i. A common error that students will make is when they're expanding a binomial, that they're just going to write this as 6 square plus negative 3i square. And of course, that's not correct if we have a square on the outside of a binomial type. What we're going to do is we're going to turn this into a FOIL problem by rewriting this as 6 minus 3i times 6 minus 3i. And then we can go ahead and we can do our first, our outer, our inner, and our last. So 6 times 6, 36. 6 times negative 3i, negative 18i. Negative 3i times 6 is another 18i. And then finally, negative 3i times positive 3i is negative 3i times negative 3i becomes a positive 9i squared. Basically, what we've seen is that I square just changes the sign in front of the real coefficient. So another way we could write this is 36 minus 36i minus 9. And then finally, what we can do is we can combine the constants together. And so we're going to wind up with 27 minus 36i. If we divide complex numbers, what we're going to do is we're going to multiply. If we just have a single I in the denominator, we're going to multiply the top and the bottom by I, right? And what this is going to do is it's just going to turn it into the form to where we don't have any i's in the denominator, all right? And so we have our 6 over I, and we're going to multiply that by I over I. And one question you might ask is this legal? Okay, well, the reason it is legal is because I over I is really 1. In fact, anything divided by itself is 1. And if you multiply anything by 1, that's an identity. All right, and that's okay because we're not changing the original problem. All right, so just making sure that everybody understands why it's legal is because we're just basically multiplying by a different form of 1 in this instance. And so if we multiply through, the numerator becomes 6i, the denominator becomes I square. We know that I square is negative 1. And if we divide 6 by negative 1, that's going to be minus 6i. So it's actually pretty easy for us to be able to divide these sorts of complex numbers, or in this case, imaginary number, if we just have a single I in the denominator. Now, if we have 2 terms in the denominator, like an a plus bi, then instead of multiplying by I, we're going to multiply by the a minus bi. So we're just going to change the sign in the middle. And subsequently, if we have an a minus bi, we're going to multiply by a plus bi in the numerator and denominator. That's called multiplying by the conjugate. All right, and we're going to see that as we go out through our mathematical careers, we're going to see that the conjugate is a powerful tool of rewriting lots of different expressions, even in trigonometry, in calculus. We can do it even higher than calculus sort of stuff. But we're just going to go through in this and just illustrate how we can go through and divide something like 6 over 4 minus I. All right, so we're going to start. So this is the original problem. And we're going to multiply this by 4 plus I over 4 plus I. All right, and again, that's just called multiplying by the conjugate. It's helpful to put parentheses around any of the binomial sorts of numerators or denominators. All right, and you could treat it basically like a polynomial multiplication at this point. So another way to write this, if it helps you to think of it as 6 4 plus I over 4 minus I times 4 plus I. Right? And then we're going to go ahead and distribute the numerator. So that becomes 24 plus 6i. The denominator is a little bit more lengthy because it's a FOIL. First, outer, inner, last. 4 times 4, 16 for the first. 4 times I, positive 4i. Negative I times 4 is a minus 4i. And then finally, negative I times positive I is a minus I squared. And you might be thinking, well, how does this make it any better whatsoever? In fact, this looks like it's even uglier than what we started with. But the good news is that by multiplying by the conjugate, those inner terms cancel, And remember, I square is really -1, and we have the opposite of -1. So now we can write this as 24 plus 6i divided by 16 minus a -1, or 24 plus 6i divided by 17. And the instructions tell us to write it in the standard form, a plus bi, if necessary. So we're going to write this by just dividing it out into two separate terms. So this is going to be 24 over 17 plus 6 over 17i. And notice what this does is that there's no i's in the denominator any longer. All right, so we basically divided it out. One last example of this, we have 3 plus 5i, 1 plus i. And we're going to do the exact same thing, except we're going to change the conjugate this time into 1 minus I over 1 minus I, okay? And again, it's probably helpful to change everything into parentheses for binomial types. We're going to have to FOIL in both the numerator and the denominator for this one. So 3 times 1, 3 times -i, 5 times I, 5i times 1, and then 5i times -i. So this becomes 3 minus 3i plus 5i minus 5i squared in the numerator. In the denominator, 1 times 1, 1 times -i, 1 times 1, and I'm sorry, 1 times, I already multiplied the ones together, so it seems like I'm just trying to multiply the ones several times, which really doesn't help us. It'll be I times 1 and I times -i. All right, so in the denominator, 1 times 1, 1 times -i minus I times 1 is a positive I, and then finally I times -i is a -i squared. All right, now we do have some simplification to do. All right, in the numerator, we have a -3i and a positive 5i. So we can rewrite the numerator as 3 plus 2i. And then remember, I squared just changes the sign in front, and that's going to become a plus 5. In our denominator, i's cancel out, and we have an I square, which is 1 times -1, so we get 1 plus 1. Right? We could simplify further into 8 plus 2i over 2. Just like before, we could split it up as 8 over 2 plus 2 over 2i. And then finally, we could simplify each of those completely, 4 plus I. And that's a lot better looking than this original expression of 3 plus 5i over 1 plus I, right? So we're going to take a look at one more video after this where we just solve quadratic types of equations that have complex sorts of solutions. And we're going to see why we actually need complex numbers in our next video.